So now coming up on the last two problems, question 5. This should look pretty familiar from the note packet. This is very similar to the last problem in the note packet, where we have a pivot point that's away from the center of mass of the board. And then ultimately what we're trying to find is the unknown mass. So this is clearly a torque rotational equilibrium problem. So coming down to the diagram, I'm going to highlight some important points. Defining the coordinate system and choosing the positive direction. Again, this should be like the first thing that you do for these problems is define those two things, because that's going to dictate the signs. Then over here, I've got my rigid free body diagram. And so let's point out some of these components. I have designated the X as the pivot point or the axis of rotation. And so now we can label our distances from the pivot point to the various forces, because we're going to need that distance when we determine the torques that those forces cause. So how many forces are acting? Well, we've got a 20 Newton force downwards on the left-hand side, so that's over here. We have the weight of the board. So since the pivot point is off axis, the weight of the board is going to apply a torque. So that's over here to the right of the pivot point. We have a 30 Newton force pointing upwards away from the pivot point. That's this FR over here. And then finally, we have this unknown mass that we're placing on the end of the board. And that's going to apply a weight force downwards on the board. So you may just think, okay, that's all the forces acting. And then one thing that's easy to forget is that we have a force acting upwards from the pivot point acting on the board. So the board is our system. So the only forces that we should draw on our rigid free body diagram are the forces that are acting on the board. Any force that is from the board, like normal forces acting on, say, this mass here, those should not be included in your rigid free body diagram. It's only forces acting on our system, like all of our other free body diagrams. And so it's only forces that are acting on the board. So we have that one more force, that pivot point, force from the pivot point acting on the board upwards. That's an easy one to forget, especially in an exam setting where you're kind of rushing a little bit. Is that force causing a torque on the board? So you should automatically be saying no, it's not, because it's acting at the pivot point. Forces acting at the pivot point do not cause a torque. Why? Because if you go down here mathematically, the radius from the pivot point is 0. So the torque is 0. And intuitively we know this. If we press at the hinge of a door, we can't cause the door to rotate. And that's because it's acting at the pivot point. So this, how to solve this problem, follows exactly how we've done all of our other torque problems from the note packet, the homework, and the lab. We've had a lot of experience with this. Pretty much always we're going to have to sum the torques and sum the forces acting. We're going to have to use both to be able to determine whatever it is we're looking for. So that's the pretty standard prescription. Sometimes you might be able to get away with just summing the torques or just summing the forces, but more often than not, you're going to have to do both. So that's what we're doing down here. To find the mass, we are summing the torques that are acting about that pivot point. There are 4 forces that are away from the pivot point, so we're going to have 4 torques as a result. All of our distances are 90 degrees to the forces, so the sine of theta is sine of 90, which is equal to 1. So as long as you designate that, I'm good with that. You don't have to write out sine of 90 for each one. But if you want to stay consistent and you want to just be really methodical about it, which I do encourage, feel free to do that as well. The only reason I didn't do that is just to save space, really. And then to be able to determine the force by the pivot point, we determine the unknown mass, so we can determine the unknown weight at the end. And then we have values for our 4 forces away from the pivot point. Once we have those 4 forces, then we can just sum the forces in the y direction. It's not moving up and down, so it equals 0. And then we can solve for the unknown force at the pivot point. And so this is a pretty standard problem. You can expect to see something very similar to this on the exam. And then finally, this is more of a challenge energy problem. This level of difficulty, though, is something that you could see on the exam. It's the bulk of the work is drawing your picture and knowing what's going on. Once you have identified your initial and final areas, it's a pretty standard problem in terms of dealing with energy conservation. So what we have is we basically have this bungee jumper. So we've got a person that's up on a diving board. They jump up off of it, and they're basically bungee jumping down to the ground. So they start with some velocity because they're jumping on a diving board. They are above the ground, so they have potential energy. And then they're falling through the air. So they're gaining kinetic energy, losing potential energy, and they're attached to this bungee cord. So that can just be represented as a spring. And ultimately, that's what we're looking for. How stiff of a bungee cord do we need to get the physical scenario to happen? So what we want is to barely not touch the ground. We want to extend all the way to the bottom to ground level. What stiffness of a bungee cord do we need? So we need to solve for K, which is the spring constant. So what we have, like I was saying, is we're falling through the air, so we're gaining velocity, gaining kinetic energy, losing potential energy, and then ultimately we're transferring our kinetic energy into spring potential energy. So that's what we have here in the diagram. We're falling in free fall for 75 feet. And that at that point, once we hit the 75-foot mark below the starting spot, that's when the bungee cord starts to stretch. So the key here is that we're not going all the way down to the ground. We can't go all the way down to the ground, or else, well, we would hit the ground, because a person has some height associated with them. So that's why we need to account for this 6 feet down here. This is the 6 feet of the person. And so we want to make sure that in terms of our stretching distance for a spring, we're not including that distance because we want to make sure that Cody survives this jump. If we take this 25 as our whole stretching distance, then Cody is going to be stuck to the ground, and that's not going to be too good. So I've identified the initial and final spots for our energy consideration. I've got a coordinate system defined with a 0 point for potential energy, which is the ground. And so let's take a look at our energy equation, see which ones drop and which ones don't. Like I said, you start with potential energy, gravitational potential energy because we're starting above the ground. We're starting with kinetic energy because we jump off the board. There's no air resistance in this problem, so there's no work done by conservative forces. The bungee cord is unstretched for the first 75 feet because we're acting in free fall, so the spring potential energy is 0. At the end, depending on where you choose your potential energy point as 0, I chose it at ground level. So it's going to have some potential energy at the ground because we are 6 feet off of the ground at the end. We're going to have spring potential energy because, well, the bungee cord's stretching. We better hope we have spring potential energy because, well, that kinetic energy better go somewhere. And so we're hoping to just reach the ground. So at this point, and you can watch a bungee cord video, you'll see at the very end, there's this crossover point. They're moving downward, so they have a negative velocity. And then there's a point where everything stops, and then they start to go back up. And that's when they start having a positive velocity. And so there must be a turnaround point, and at that turnaround point is what we're looking for. And that's a kinetic energy of 0 because the velocity is 0. So now that we've identified what our initial and our final energy considerations are, we can go ahead and solve the problem. So you can do two things. You're given everything in feet. So you can go ahead and convert everything into meters if you want. But there's nothing stopping you from just sticking with feet and seconds to solve this problem. And that's how I ended up doing it. The key here is that you're going to have to convert G, 9.8 meters per second squared, into feet per second squared. But we all know how to go from feet to meters. So it's just one conversion meters to feet. So it's only one conversion if you keep everything in feet. There's a lot more conversions if you convert back to meters from feet. But there's nothing stopping you from doing that. That's pretty straightforward. And it's good practice because, the final's coming up and that could be something that shows up. So I started with the energy equation, separated everything out, and solved for the spring constant because that's ultimately what we're looking for. We don't know the mass at this point, and we're going to need it for the gravitational potential energy and the kinetic energy. And so this is where the unit conversions come into play. We're given the weight. Cody weighs 170 pounds, so we can solve for mass, and this is where the conversion came in, converting G to 32 feet per second squared. Substituting all of that in, you find K is equal to 90 pounds per foot, and then down here is just a check for units and whether it makes sense.